All right, I think we'll get underway. Hopefully, we get a few more people that come in. I know there were a number of people that were interested that I don't see them here. So, in any event, we have a very distinguished group of speakers that are very knowledgeable on this particular topic. We have John Carroll. He works at the National Carbon Capture Center in Alabama, which is administered by Southern Corporation. That's why you would see his email as Southern Corporation. But in addition to that, we have Damien from 8 Rivers. He has a company that is collaborating. In fact, you see all three of these people are collaborating. They've got a lot of interrelated activities. But 8 Rivers has a technology that they will present today on carbon capture that is kind of very unique, and it might give you a new perspective on what you can do with coal or any other hydrocarbon biofuels. And then also we have Peter Rice from Siemens Energy. Peter is very knowledgeable about so many topics, and he will be on our panel session. So let me start. Probably no doubt ARC has shown you this slide and a number of other presentations because we did a lot of data gathering. But if you look at the things that are changing manufacturing, we says, well, it's artificial intelligence, cloud infrastructure, and clean energy technologies. Those are the top three. But of course, if you think about all of this artificial intelligence and machine learning, they are computed in data centers, and data centers need electric power. And so we're talking about one of the opportunities for data centers that might want to get power. And there's no shortage of data centers that are looking for contracts with reliable power to power their future computing needs. And of course, we also are talking about clean energy technologies. So we're trying to describe, we're trying to solve the problem of how can you provide all of our energy needs and not put out CO2 and other pollutants. So in any event, these are the companies that you have. I put some of the logos up there: 8 Rivers, National Carbon Capture Center, and Siemens Energy. Let's just start with and we're also going to have some discussion on hydrogen, although most of our remaining talk will be on carbon capture. But we also do want to mention hydrogen because it's related, and certainly blue hydrogen is a carbon capture technology, for example. But carbon capture and storage has kind of a reputation, and maybe we can get some adjustments depending on different technologies, but roughly speaking, to build a power plant that captures the CO2 requires 30% more capital investment and consumes maybe up to 20% of more gas compared to a natural gas power plant that has no carbon capture, right? So carbon capture and storage is expensive, both from an operating and capital point of view. And so obviously technologies need to focus on addressing that challenge. So the challenge with green hydrogen is that currently green hydrogen costs roughly $15 a kilogram to make. There's a tax credit for about $3 a kilogram, which brings it down to maybe $12, or in some cases maybe as low as $9 a kilogram. But you can get gray hydrogen for $3 a kilogram. Well, as long as you're not penalized or required to consume green hydrogen, if you have a choice between $12 a kilogram and $3 a kilogram, certainly at the grocery store, you're going to make a decision for 3, right? So green hydrogen has kind of an economic penalty. I know that the Department of Energy has hopes to get the cost of hydrogen down to $1 a kilogram. There's a number of factors at play. On the one hand, you can have government incentives and grants and other things that help to subsidize hydrogen to make it cheaper. And there are other possibilities of having regulations and maybe a carbon tax that make some of the alternatives more expensive. And today, basically, we see that many of the green hydrogen plants that come in, they have no market for their product. They could make green hydrogen, but they can't get a sustained commitment to purchase that. However, let's take a look at the opportunities. We know carbon capture and hydrogen are both likely to play a huge role in the future. We are right now at the beginning. Currently, of all of the CO2 being emitted in the world, carbon capture accounts for 0.1% of is captured. So it's a pretty small percentage. There's plenty of opportunity to capture CO2 at a lot of different smokestacks and power plants and boilers and heating systems, et cetera. We make about 100 million tons per year of hydrogen today. The vast majority of that hydrogen is used in refineries for desulfurization and hydrocracking and or ammonia. About 90% of all hydrogen goes to those two uses. Maybe 10% goes to some other uses like methanol and other consumptions. However, out of 100 million tons per year of hydrogen in 2023, about 2 million tons of blue hydrogen are made, but only 0.1 million tons per year of green hydrogen is being made. So you can see green hydrogen is still way at the bottom. Now, U.S. government support certainly can play a role. There are a number of CO2 demonstration projects. In order for carbon capture to work, you need to first capture the carbon at its source point, and that could range from power plants to boilers and other things. And you need to be able to transport that to a location where it can be injected in the well. The vast majority of carbon capture today is used for enhanced oil recovery. So you capture the CO2, but you can inject it in depleted wells or producing wells to extract more hydrocarbons, right? The other possible way is to store that into what's called a Class 6 reservoir, of which there are only a few of them. There are not that many. I think there's only 6 of them, roughly, as I recall, certified in the U.S. to accept CO2 for long-term permanent underground storage. And if you were to use that, you would be able to get a tax credit, a 45Q tax credit of $85 a metric ton of CO2. And if you use CO2 for EOR, enhanced oil recovery, you would get $60 a metric ton. In any event, we'll be using an awful lot of abbreviations. I know in my presentation I tried to put what the abbreviations mean because it's very hard to keep up with them all. But if you have any questions about abbreviations, we can get to them. So the current 3 largest CCUS projects are this Petrobras project, an Exxon project, and a Longfellow project. All right, and you're looking at 10 million tons, 7 million tons, and 5 million tons, and a number of those are. I don't remember which ones. I think one of actually might use a Class 6 reservoir, but I think most of the projects today are injecting CO2 into existing oil wells for enhanced oil recovery. So let's switch over and talk a little bit about hydrogen. And I wanted to make sure that I put the hydrogen colors a little bit fuzzy, all right? Because if you're said, well, I'm just going to get electricity from the grid and I'm going to make hydrogen with an electrolyzer, well, there's a lot of questions about when and how that electricity was made and whether it's green. And it's pretty unlikely that you're going to take a electrolyzer and just make hydrogen during the times it's sunny or during the times it's windy. Those electrolyzers are a big capital investment. They typically need to run 24/7. So the green has some questions about it. Gray hydrogen, has a range of activity, sometimes mixed in with the term black. It could be made from different types of coal and different types of natural gas. And some of those have the same problem that blue hydrogen has. One of the problems with first of all, blue hydrogen is basically steam methane reformed hydrogen. We take water and natural gas, we heat it up in a catalyst, and then we capture the CO2, all right, typically. And we manufacture hydrogen. That's how most hydrogen, that's how blue hydrogen is made today. But blue hydrogen also has a few other issues, and I think we'll get to them. Probably you never heard of a hydrogen called turquoise hydrogen, but it is possible to take natural gas and in a pyrolysis process to pull the hydrogen off of the carbon, but instead of making CO2, it makes graphite or graphene or some other carbon-based things. No CO2 emitted. There are a number of companies that are working on such technologies, and it has some thermodynamic advantages in principle. It would take less energy, but so far that technology has not quite taken off. But there are people working on it. They think it might work. They kind of use the term pink hydrogen because it's, there's been a lot of proposals from the new small modular reactor companies that say, hey, we can make hydrogen along with nuclear power. We can integrate the hydrogen production here. We can use molten salt and a number of other characteristics to make hydrogen from nuclear power. And there is a white hydrogen. There have been some discoveries of hydrogen just coming out of the ground. In general, this is not likely to be coming from natural gas wells. The places they have found hydrogen are much deeper in the ground, and they're not coincident with natural gas drilling. And the few little repositories of white hydrogen so far have not really made any significant dent. But it's a dark horse in the race for which hydrogen color is going to win. All right. So let's talk a little bit more about hydrogen. So here you see electrolytic cells. We will describe a couple of different electrolysis type cells. And here you see a simulation of a steam methane reforming. As I mentioned, they are taking water and natural gas. They're heating them up in a furnace using gas or oil or something to heat that furnace. And they are using the water gas shift reaction to basically make an intermediate syngas with carbon monoxide and hydrogen and the water gas shift reaction. And ultimately they make hydrogen coming out. And if you're going to capture that, it's often done bolted on the outside, post-combustion carbon capture. Both of these processes are endothermic. That means they take energy has to go in order to break the bond. There's a fundamental difference between electrolysis because you're breaking a hydrogen-oxygen bond compared to steam methane reforming, which is a carbon-hydrogen bond, all right? And so if you actually look at the enthalpy of the reactants and the enthalpy of the products, there's a fundamental problem in that you must put this much energy. Catalysts don't save you. 100% efficiency of electrolyzers does not get past this rule. You simply must put in a certain amount of energy in order to break those bonds and end up with hydrogen coming out. And you'll notice that water electrolysis, 286 kilojoules per mole, and is a little bit more, considerably more than steam methane reforming. And this pyrolysis, which is one of these dark horses, in principle could be done here. Now these are the ideal, perfectly 100% efficient, no heat loss, no energy loss, perfect, doesn't take into account any energy to purify water for electrolysis or energy lost in the rectifier putting power or the energy to compress hydrogen or liquefy hydrogen, for example. And obviously, there's lots of other inefficiencies along the way. So, sometimes we hear great potential and lots of, maybe some people call it hype for hydrogen. And the interesting thing is that hydrogen can do virtually anything that any other energy source can do. We can make electricity from it. We can run it. We can run buses, trains, planes, rockets on it. In principle, you could put a home electrolyzer in and have hydrogen to fuel your car, all right? I'm not sure I would do that in my house, but nevertheless, it's possible that you could have this great hydrogen infrastructure. And you could heat processes, you could heat buildings, you could heat homes, you could store hydrogen as a liquid or a compressed gas or in a metal hydride. You can generate electric power either in a gas turbine that can burn hydrogen. I think Peter knows about that issue very well because Siemens Energy is very big in gas and steam turbines, and he knows all about that. All right. But the other thing is, if you had hydrogen, you can convert it to other fuels. Hydrogen is a fundamental building block to make ammonia. So if you have hydrogen, you can make ammonia. If you have hydrogen, you can make methanol or ethanol. If you have hydrogen, you can make synthetic aviation fuel by reacting it with CO2 from the air and having a net negative carbon footprint. You can also make e-gas and e-diesel. Porsche advocates this big e-gas plant down in South America that says we are going to make gasoline for our fabulous Porsches, and we're not going to give up our beautiful engines. So in any event, if you look at all of these things, you could say, well, hydrogen can work everywhere. We don't need anything else. You'd hardly need electricity even, except to make the hydrogen, all right? So, the vast majority of hydrogen is made in alkaline electrolysis. This is very similar to the chlor-alkali process, basically. Uh, this is the most common electrolyzer. Then there are, PEM, polymer membrane electrolyzer. I think Siemens makes some of those. And I think the PEM might need a little bit higher purity water. Alkaline is a little bit more tolerant of the water purity going in to prevent the still runs. Probably the most efficient of these designs. The anion exchange membrane is kind of a newer technology. There's very little of that out there yet. It might combine the best of the first two. And then solid oxide electrolysis cell, instead of taking water with electricity, we take steam. And by taking steam, you've already put enough energy to make that phase change between liquid and gas. And so you start out with a higher enthalpy feedstock, and therefore you can save at least that much energy in the system. And a lot of the nuclear power plants say that, we can build hydrogen with the SOEC type design because we have a lot of waste heat. We can preheat water, make it into steam. And so that they kind of look at that design. And that's going to establish technology, but it's still, alkaline is the number one actual production. So if you look long term where hydrogen could go, you can see on the left hand side we've got 70 billion tons per year. 70 billion tons per year. What do I have kilograms per year? Billion kilograms. One of those units is wrong. But let's say we have 70 billion tons per year. On the left is the existing production, primarily ammonia and refining. If, however, long term in the future, we would need much less for refining, but cement and steel would need much, much more hydrogen than is even used for ammonia. And so if you were to really to shift to hydrogen for all of those industries 100%, you would have a much larger need for hydrogen than we have today. One of the companies I do follow is Rystad Energy, no relation to me, RYS. But they kind of see that, blue hydrogen is here now, but green hydrogen eventually is projected to overshadow and catch up and surpass blue hydrogen. And you can see different countries, Asia on the left, North America and Europe are the biggest hydrogen consumers. And you see that the US seems to be a little bit more focused on blue hydrogen according to their market analysis. A few years ago, we did a market study here. I did a market study here for ARC on all the electrolyzer suppliers, and what we find is this list of substantially Japanese suppliers. I mean, Siemens Energy is on there, I think, but most of those electrolyzers are designed and built in, not necessarily designed in China, but built in China. Cockrell was a Belgian company, and I think they just asked the Chinese to build it for them, and then they had a joint venture with Jingli, all right? ThyssenKrupp is a well-known and established supplier of electrolyzers, and they've actually built electrolyzers for chlor-alkali plants. If you look at the total megawatts of chlor-alkali plants, it's far more megawatts of electrolyzer capacity is in chlor-alkali plants than hydrogen so far, all right? How this unfolds, we'll see. So in terms of clean energy tax credits, there's a 45V tax credit. That's basically $3 a kilogram for clean hydrogen. Department of Energy is also providing lots of different incentives as well. So let's just kind of close with the overall challenges and opportunities for CCUS and hydrogen. So the challenge is that CCUS is expensive. It has to compete with SWB, which is solar, wind, and batteries, all right? So, and nuclear power. So it has to compete with other sources of energy and be able to produce this, particularly for making power, all right? We are missing the CO2 pipelines and Class 6 storage sites. We have to overcome that high CapEx and OpEx compared to conventional power plants. But again, there's opportunities with government incentives. There are data centers that are desperate for power. We want you to build a power plant right next to our we want a data center, we want you to build us a power plant, and we'll pay a premium for that. And carbon capture and storage certainly is an option for that. There are also climate goals for reducing greenhouse gas emissions, and it may eventually be incentives such as a price on carbon or other things that might make carbon capture even more expensive. Electric grids require peakers. electric grids are struggling. We got all this solar and wind coming on. It's all non-dispatchable. They are trying to figure out how they can keep going their power 24/7. And so there's a lot of planning and logistics from all the ISOs and RTOs across the country to figure out how they can compensate and emphasize and monetize or encourage companies to build power plants that can deliver peak power, dispatchable peak power, which CCS is certainly an option. In any event, I think I had one more slide here. How come I'm not clicking? Can you click me? All right. In any event, that's the end of my presentation, and we're going to bring up John Carroll.